Good afternoon, my dear students. My name is Dr. KCH Apparao, working as an associate professor in mechanical engineering department. Okay, in the previous class, we discussed the critical thinking questions and different important derivations. We already discussed one-dimensional steady state conduction equation in slabs. We discussed one-dimensional steady state conduction equation in cylinders. Also, we discussed this one. So by using those formulas and single slab and a single cylinder or composite slabs and composite cylinders, okay, we'll solve different numericals which are based upon the cylinders and the slabs mainly. Okay, so problem solving and question banks which are given in the question bank. So we'll solve those questions. Problem solving and conduction process we'll see first of all. So in the previous class, we already discussed for the slab rate of heat transfer, a one-dimensional rate of heat transfer, heat conduction equation in a slab, that is Q is equal to Ka into T1 minus T2 by L. We already derived in the previous class. Suppose if there's many layers are there, that rate of heat transfer in composite cylinders we already discussed. That is that nothing but suppose if you take two layers, then initial temperature Ta minus Tb by if you consider the convection process also 1 by Ha plus L1 by K1, L2 by K2 and 1 by Hv. So already discussed in previous class, you can see. Okay, there are two layers and just like this is the hot fluid to inner layer, next to inner layer conduction, next layer conduction, next to so last layer to atmospheric convection process. So these are the formulas. You can refer the previous class to solve the numericals. Okay, so these are the one-dimensional heat conduction equation for a single slab, one-dimensional heat conduction equation for the composite slab. So this is the formula that is the one-dimensional heat conduction equation for the cylinder. So 2 pi KL into initial temperature minus final temperature by ln R naught by Ra. Okay, you consider hollow cylinder like this one. So inner temperature Ra, outer temperature radius R naught, inner radius is equal to Ra. Inner temperature is equal to Ta, outer temperature is equal to T naught. Length of the pipe, hollow pipe is equal to L. Then this is the formula. Rate of heat transfer in this type of hollow cylinder. Okay. So Q is equal to 2 pi KL into Ti minus T naught by ln R naught by R. This is the formula. So this is the formula for the single cylinder. Then if there are composite layers, there's many types of different layers are there, then you can take this formula for the rate of heat transfer or one-dimensional heat conduction equation in different layers. So Q is equal to 2 pi L into hot fluid temperature minus cold fluid temperature, initial temperature minus final temperature by all the thermal resistances. This is the thermal resistance based upon the convection process. This is the thermal resistance based upon the conduction in the first layer. This is the thermal resistance based upon the conduction for the second layer, layer B. This is the thermal resistance based upon the convection for the last layer to outer layer surface to atmospheric. So we can refer those things. So by using these formulas, you can solve different numericals which are given in the question bank. We'll see first one. A steam pipe 200 mm OD is covered with 25 mm thick layer of insulation material. Okay. Thickness of the insulation material is equal to 25. So This is the red portion that shows the insulation material. This is the inner, that is the hollow pipe, okay, steel pipe or steam pipe. Okay. So outer diameter of the hollow pipe is given. That is the, you can take outer diameter of the hollow pipe is nothing but inner diameter of the layer insulating material. You can take like this one. Ri is the outer diameter of the pipe or inner diameter of the insulating material. Okay, Ri is equal to 200 mm, or radius is equal to 100 mm. Okay, you can convert it to meter, 0.1 meter. Next to average thermal conductivity of the insulating material also given. That K for insulating material, that is the 0.08 watt per meter Kelvin, watts per meter Kelvin. The temperature of the pipe surface, so outer pipe surface is equal to given, then you can take that is the TA. TA is equal to 400 degree Celsius. Okay. Similarly, outer surface of the insulation. So this is the here outer surface. So this is the you can take T naught. T naught is equal to 50 degree Celsius. Right? Find the loss of heat. Find the loss of heat for a length of 10 meter. So L also given. L is equal to 10 meter. Okay. So you have to find out the Q value. Q. Okay. Here given, you can see this one. These are the given data. Thermal conductivity of the insulating material, insulation material, 0.08 watt per meter Kelvin. Inner radius of the insulating material, 100 mm, at 0.1 meter. So outer radius of the uh, insulating material, that is the inner radius plus so thickness of insulating materials, 125 mm, that is equal to 0.125 meter. So length of the pipe also given, inner temperature of the insulating material, outer temperature of the insulating material. So these are the given data. By using this data, you can find out the rate of heat transfer. Heat loss E is equal to. So area, area is equal to 2 pi KL into temperature difference. T I minus T naught by T naught by ln R naught by R. So this is the formula. You know all the things. So 2 pi the constant is thermal conductivity, K also known, L is equal to 10 also known, Ti temperature, inside temperature also known, outside temperature also known, and R naught by Ra also known. If you substitute all these values, you will get the answer. So this is the formula. You can refer this one. U is equal to 2 pi K L into Ti minus T naught by ln R naught by R. Okay. If you substitute all the values, you get the final value. So 7,884 watts. Okay. Let's see one more numerical. Water enters a pipe at a temperature. Pipe temperature of the water. Pipe of water enters a pipe at a temperature of 60 degree Celsius. So water temperature is equal to given. Assuming pipe is made of stainless steel, pipe thermal conductivity of the pipe also given. K is equal to 30 watt per meter Kelvin. Okay. That the pipe has an inner and outer diameters. Inner diameter, that is the Di is equal to 20 centimeters. D naught is equal to 25 centimeter also given. So what is the outer temperature of the pipe? So inner temperature of the pipe is given Ti 60 degrees Celsius. We have to find out T naught. So rate of heat transfer, heat is lost at the rate of kilojoule per kg Kelvin. So it means Q also given, that is 15 kilojoule per kg meter second. Assuming temperature is constant down the length of the pipe. Okay. So you can solve this one. Okay. So here also just like same formula. That is the cylinder formula, single cylinder. Thermal conductivity of the cylinder also given. That is the K is equal to 30 watt per metric Kelvin. Okay. So this is the formula, you know that one. Q is equal to 2 pi K L, Ti minus T naught, ln R naught by Ra. Here Q also given, and T naught you have to find out this one. Q is given, that is the 50 kilojoule per, so kilowatts, 15 kilowatts means 15,000 watts. Okay. So Q value, you know this one, you can substitute this one. 2 pi into K, thermal conductivity. Thermal conductivity of the pipe is equal to 30 watt per meter Kelvin. Okay. So next to length is equal to 1. You can take unit length, and inner temperature is equal to 60 minus outer temperature T naught. You have to find out this one. ln R naught by Ri. R naught is equal to 25. Ri is equal to 20. So you can take diameter by diameter or radius by radius. You can take. If you solve this one, you will get T naught value. T naught is equal to just like 42.2. Okay. So in this way, just like you can solve the different numericals. Now let's see one more numerical which is given in the question bank. Okay. Yes, to steel tube, the material is the steel. So thermal conductivity of this tube is equal to given. K is equal to 43.26 watt per meter Kelvin. So steel tube of 5.08 centimeter inner diameter. Okay. Inner diameter temperature diameter has been given. That is the D1 or DI. You can take anything. So D1 is equal to 5.08 centimeters. So you have to convert it to meters. Okay. So then R1 is equal to just you can convert this one 2.54 centimeters. Convert into meters. That is 0.0254. So that is the meter. Next to inner diameter and outer diameter also given. Outer diameter uh, D2 is equal to given. That is the 7.62 centimeter. That is called 0.0762 meters. The radius of the outer diameter R2 is equal to 0.0381. Okay. So this is the inner diameter, outer diameter. Next to the steel tube is covered with a insulation layer of insulation. Thickness of the insulation also given. Okay. So you can take that is the R1 inner diameter radius, R2 outer diameter of the steel tube, R3 is the just like outer diameter of steel tube with insulation material. It means R3 is nothing but R2 plus thickness of insulation material, that is the 0.025. Okay. That here. So thickness of insulation, that is the R3 is equal to R2 plus thickness. So 0.0381 plus 0.025. This is the R3. Okay. So here you can see one is the steel tube, another one is the layer. Okay. So you can next to a hot gas at a temperature, hot gas temperature TA, hot gas temperature at TH 318-316 degrees Celsius. Ambient temperature TB is equal to 30 degrees Celsius has been given. Okay. Next to heat transfer coefficient for the hot fluid temperature. So that one also, it means HF, hot fluid temperature. So that one also given. That is the 28 watt per meter square Kelvin. Similarly, heat transfer coefficient in the cold fluid. So that one also given. That is the 17 watt per meter square Kelvin. So calculate the heat loss. So Q, we have to find out Q. Heat loss for 3 meter length of the tube. So length of the tube also given L is equal to 3 meters. Okay. We can solve this one here. These are the given data. Thermal conductivity of insulation K2 given. Hot gas temperature TA given, convert into kelvins. Ambient temperature, air temperature TB 30 degrees Celsius, convert into kelvins. Heat transfer coefficient in inner side. So hot fluid side, inner side heat transfer coefficient, that is HA is also given. Next, heat transfer coefficient outer side of the pipe. So that one also given, that is the 17 watt per meter square Kelvin. Length of the pipe also given. Okay. Then you can solve with the numericals. Here, one is the steel pipe, another one is the insulating material. Two layers you can. One is the steel pipe layer, another one is the insulating layer. So here, it means just like this is the numerical based upon the composite cylinders. Okay. So for the composite cylinders, you know the formula Q is equal to just here also given. You can take Q is equal to initial temperature, hot fluid temperature minus cold fluid temperature, TA minus TB, by thermal resistance with respect to inner surface convection, outer surface convection, inner tube, it means so steel tube conduction, and the insulation material conduction. You have to consider all these thermal resistances. This thermal resistance with respect to convection process in inside hot fluid to inner surface. This is the uh, outer surface to cold fluid. Okay. So this is the convection. Two convection thermal resistances, two conduction thermal resistance. One thermal resistance of steel tube, another thermal resistance of the insulating materials. You know the formulas were already derived in previous class also. So 1 by 2 pi R1 L into, okay, HA, hot fluid heat transfer coefficient. So ln R2 by R1 2 pi K1L, ln R3 by R2 2 pi K2L plus 1 by 2 pi R3L HB, hot fluid coefficient of heat transfer of outside surface. So you know all the values. You know the hot fluid temperature, you know the cold fluid temperature, R1, R2, R3, you know this one, K1 also, K2 also given, thermal conductivity of the steel pipe given, thermal conductivity of the insulation also given. So you can substitute all the values, then you will get rate of heat transfer. Okay. So heat loss. So Q is equal to the final value is equal to 1129.42 watts. So in this way, just like you can solve the different numericals which are based upon composite slabs or composite cylinders also. Okay. Let's see one more numerical. A wall. So this is the numerical related to composite to slab. A wall. This is the wall. The thickness of the wall 0.5 meter is to be constructed from a material which has an average thermal conductivity. So this thermal conductivity given also given, and the wall is insulated. Another material, that is the insulating material. Thermal conductivity of the insulating material also given, and just like so that the so per square meter heat losses value also given. Q is equal to 1450 watts, assuming the inner and outer surface temperature. Here temperature T1, here outer surface temperature T2. You can take, okay. So those temperatures also given, 1200, 15 degrees Celsius. So calculate the thickness of insulation material. So L1 given, L2 how to find out. Okay. T1 given, T2 given, K1 given, K2 given. Okay. So you know that rate of heat transfer for the composite slabs. So Q by A is equal to heat flux. Initial temperature T1 minus final temperature T2. Otherwise, if you want to take it, this is the T1, this is the T2, this is the T3. Then the temperature difference means T1 minus T3. Otherwise, you can take directly, this one is the T1 inner, outer is equal to T2. Okay. So initial temperature minus final temperature by thermal resistances. Thermal resistance of the first uh, plate wall, next to thermal resistance of the insulating materials. That is the L1 by K1 and the L2 by K2. Okay. So here this value has been given T1, you know that T2 also given, L1 given, K1 given, K2 given, L2. You have to find out the L2 values. Okay, here you can find out like this one. So by substituting all the values here, then you can find out the L2. So in this way, just we can solve the different numericals which are based upon the uh, conduction of slabs and cylinders. So here just we discussed the few numericals which are based on the uh, one-dimensional heat conduction in the slab and one-dimensional heat conduction in cylinders and cylinder. Next to one-dimensional heat conductions in different layers of slabs. It means composite cylinder, composite slabs and composite cylinders. Okay, so these are the numericals. You can solve different numericals which are based upon this one. Okay. Here, just a graphical representation of this numerical also given. You can see that one also. So this is the graphical representation. So this is the temperature T1, T2. You can take this is the temperature T. Thermal conductivity of first wall, thermal conductivity of the insulating material, thickness of the wall 0.5 meter, L2 we have to find out. Okay, so this is just like electrical analog formula. You can write like this one. Electrical analog is equal to thermal resistance of the first plate, thermal resistance of the second plate. Okay. So this is the T1, final is the T2, RTH1, RTH2. Thermal resistance is L1 by K1A, L2 by K2A. You know the formulas for composite walls. Q is equal to initial temperature T1 minus final temperature T2 by thermal resistance as L1 by K1 plus L2 by K2. Okay. So L1 is equal to temperature. So that is the 1200 minus 15, 1200 minus 15 by L1 0.5 meters, thermal conductivity K1. So K1 is equal to 1.4 plus L2 by Q2 is equal to 0.35. If you solve this one, so this value also given Q is equal to 1450. This is the 1450. Okay. So by substituting all this one, you can find out the L. So this is the numerical. So thank you. So these are the different textbooks. You can refer this one to solve different types of numericals. Thank you watching this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.